So now we move on to our final type of spectroscopy for now. But this is by far the most important type of spectroscopy we're going to get into. This is known as nuclear magnetic resonance, or NMR spectroscopy. Now, this is a technique you might be familiar with. In fact, you may have some experience with this. NMR is commonly used in the medical field. You may know it under its other name, MRI. So as opposed to using it where maybe you've seen it to look at a knee or other type of medical issue, we use it to look at molecules. So two types of instruments that are most commonly found for NMR. We have the picture on the left. This one. This is sort of your typical NMR. To give you an idea of size, because this picture doesn't give you a good sense of scale, this is about 5 feet tall. And if you tried to wrap your arms around the main part of the magnet, you really wouldn't be able to. They're pretty big. In addition to that, they have a computer that runs them right here. And those are probably the size of a small footlocker, maybe a little bit bigger depending on the instrument. These instruments can get even bigger depending on what they are and how they're used. And then there's a computer usually somewhere else in the room that actually runs them. What we have in our lab is what we call a benchtop Nmr. And you can see it's actually fairly small. It's about the size of a large shoebox. So there's a lot of pluses and minuses to each of these. The instrument on the left does a lot more. There's a lot more different types of experiments we can do with one of those instruments. So why do we have one of these? Well, two reasons. Number one, it does everything we need. Second, a lot cheaper. And third, takes up a lot less space. And that was the major issue, was we really didn't have room for one of the big instruments. If you're wondering about cost, at least $250,000 for one of those, versus about $50,000 or $60,000 for one of the ones we have. Big price difference. The other thing that really makes a difference with these is these larger instruments, they are cryomagnets, which means that the magnet has to be cooled all the way down to about 4 degrees Kelvin, just a couple degrees above absolute zero. Well, that means you need liquid helium. And liquid helium has gotten to the point that it can be a couple $1,000s for a cylinder of liquid helium, and for most of these instruments, you need to do that 3 or 4 times a year. So this is what we're going to be using, and it's what you'll use at whatever point you're in the lab. So what does NMR allow us to look at? Well, in reality, any atom can be analyzed. Now, in this class, as most organic chemists will, we're going to focus on 2 elements. Probably not surprising. Carbon and hydrogen. Those are our 2 most common elements. But can you do fluorine NMR or phosphorus NMR or oxygen NMR? The answer is yes. The main issue, though, is that these experiments are based on a property known as nuclear spin. And the nuclear spin is based on really the number of protons and the number of neutrons that an element has. If the spin is equal to 0, then that nucleus is not NMR active. Now for hydrogen, this isn't a concern because hydrogen 1, which is NMR active, is 98 or 99.9844% of the natural abundance. But for carbon, which has 2 common isotopes, this ends up being more of a problem. If we bring up this isotope table that we've seen previously for carbon, we can see down at the bottom we've got 2 naturally occurring isotopes for carbon, carbon 12 and carbon 13. And in this column we have their nuclear spins. So carbon 12, which is almost 99% of the natural abundance for carbon, has a nuclear spin of 0. What this means is that carbon 12 is not NMR active. And so because of this lower natural abundance, we can't always do as much with C13 as we can with hydrogen NMR. And in addition to that, if you are taking a carbon spectrum, for the same sample where a proton spectrum might take 5 or 10 scans and be done in under a minute, a carbon spectrum of that same compound might take a couple thousand scans and could have to run for several hours. So proton NMR is more widely used, and we're able to get more information from it because of its higher natural abundance. Now, before we get into what NMR shows us and how we interpret an NMR spectrum, we need to talk about what's known as chemical equivalency. Because every atom has a different way of receiving energy. And so if 2 nuclei are not equivalent, they'll show up as different peaks. Whether that's proton NMR that we're talking about, or whether that's carbon NMR. So that's the first thing we want to talk about, is how do we determine if protons or carbons are equivalent? And for right now, that's largely asking the same question. So let's start with something nice and simple. Here's methane. I'm going to label 2 of these protons as HA and HB. And the question I'm going to ask is HA equivalent to HB? Now, I think in this case we can probably pretty easily see that the answer is yes, they are equivalent. In fact, all 4 hydrogens are equivalent. But as we start to go through this, examples are going to get more and more complicated. And so is there a method that we can use which will allow us to determine, are these 2 protons, these 2 hydrogens equivalent? Or we could be asking the same thing about 2 carbons within a molecule. Well, what we're going to do is we're going to replace HA with something else. Then we're going to replace HB with something else. And let's look at the two molecules that result. So I'm going to use a chlorine here. I could have used chlorine, bromine, iodine, deuterium. Doesn't matter what I used. I just want to replace each one of those two atoms that I'm comparing with the same atom and see what happens. So you can see in the first structure, I've replaced HA with a chlorine. In the second structure, I've replaced HB with a chlorine. So the question we can ask now is, are these two the same? Are they the same molecule? And I think we can see pretty easily that yes, they are. And because they are, that means HA and HB are what we call chemically equivalent. Let's do another example. So I want to know now, are HA and HB equivalent? So I'm going to do the same thing. I'm going to replace HA with something. And then I'm going to do the same thing for HB. What should I replace it with here? Well, we did chlorine in the last case. I'm going to use deuterium here. Deuterium, being the heavier isotope of hydrogen, has an extra neutron. Are these two molecules the same? If you're not sure, let's go back to chlorine. And I think at that point we can see that clearly these are different molecules. Because they're different, that means HA is not equal to HB. They are chemically different hydrogens. Now, we could do the same thing for carbon. Here's ethane. I'm going to call these carbon A and carbon B. Now, what can we replace them with here? Well, we would need something else that can form four bonds. And so probably the easiest element to use is what we find directly below carbon on the periodic table. Silicon. So I'm going to replace the same way I did for hydrogen. I'll replace carbon A up above with silicon. And then I'll replace carbon B with silicon. Are these the same molecule? We can see here that these are the same. That means that carbon A and carbon B are equivalent. Let's do one more. So I'm going to highlight 3 of these, A, B, and C. Are they equivalent? So if we replace that center carbon, we get this molecule. We replace this one over here. We get this structure. And finally, if we do this one, we get that molecule. And I'm just going to label these so we can refer to them as A, B, and C. So this is carbon C has been replaced, carbon A, and carbon B. Are any of these the same? Well, if you take this structure here and flip it around, it'll end up being the same thing as this one. So carbon A is equivalent to carbon C. But carbon B is not the same as either of these structures, and so carbon B is different. Why does all this matter? Well, when we get to the point where we're actually looking at different carbon and proton spectra, every different carbon will have its own peak in the NMR spectrum. And so the number of carbons, the number of different carbons we have in a molecule will determine how many peaks show up in our carbon spectrum. And so let's do the following. Let's do a couple of these together, and then you've got some practice to work on. For each of these molecules, which one of these, how many different carbons and how many different hydrogens? Now, as you start to do more of these, you're not going to need to go through this process of replacing one atom at a time. What you're going to start to see, and this is what we're going to do here, is the molecule symmetric? And with pentane here, pentane is symmetric about this middle carbon. So what that means is this carbon is equivalent to this carbon. This one is equivalent to this one, and this carbon is unique. Another way to think about it is what are they attached to? So the carbon that I've highlighted in yellow is attached to 3 hydrogens and a 4-carbon chain. In order for them to be the same, that other yellow carbon has to be attached to the same things as well. So how many different carbons are there in this molecule? There are 3. What about hydrogens? Also 3. Because for now, if 2 carbons are equivalent, we're going to assume that the hydrogens on them are also equivalent. Now, the next molecule also has symmetry going down the middle. So this methyl is unique. This carbon is unique. These are equivalent. These are equivalent. And this is unique. So we have a total of 5 different carbons. How many hydrogens? Just 3. Why 3? Well, 2 of these carbons, this one here and this one, don't have any hydrogens on them. So that's why we don't have 5. What about our bottom molecule, cyclohexane? Well, cyclohexane, we can show a line of symmetry here, here, here. Pretty much any way we look at it. And so that means every carbon in this molecule is equivalent and every hydrogen is equivalent. All right, so now I'd like you to get out the exercise that looks at chemical equivalency and work through those problems.